Hello everyone, welcome back to Algebra. Today we're going to talk about group actions, which is a very important topic in group theory because of the very important applications. Let me just recap that what we just did in this course is prove the fundamental theorem of finite abelian groups. That gives me a classification of finite abelian groups. It tells me that all of them is a product of cyclic groups of prime power order and exactly how those powers come about and so on. This is very nice. So we want to do something like this for non-abelian groups, try to classify non-abelian groups, finite non-abelian groups in some form. So to do that, to be able to do the same program, but for non-abelian groups, we would have to do, well, first of all, the very first step we took was this. If we have a finite group, some G finite group, non-abelian, but just any finite group, and P divides, a prime number divides the order of the group, is there an element G of order exactly P? We proved this for abelian groups, but we didn't prove it for non-abelian groups yet. This is going to be true, and this is going to be called Cauchy's theorem. So it is true, and we're going to prove it using group actions. Now, the second part was that we defined what was P primary components, but the key part of the P primary component was that if we have a group and the order of the group is a power of P times something relatively prime to P, we found a subgroup called the P primary component of order exactly P to the R in an abelian group. And so is that true in general? If we have this decomposition of the order, is there a subgroup that has order exactly P to the R that is going to play the role of the P primary components? This is actually also true, and this is going to be what we call the first Sylow theorem. And guess what? We are also going to prove this using group actions. Okay. What about the last part? What we did to prove the finite abelian group theorem was that if we had a decomposition into distinct prime powers, we proved that G is direct product of its P primary components. And since there are groups of each one of those prime power order, is it true that G is some direct product of those subgroups of those orders? And this is false. This is false in general for non-abelian groups. For example, take G to be S3. If G was isomorphic to a subgroup of order 2, that subgroup of order 2 would have to be cyclic. Direct product with a subgroup of order 3, that subgroup would have to be cyclic. But these direct product we know is Z modulo 6, and definitely those are not isomorphic. S3 is non-abelian and Z modulo 6 is abelian, so it cannot be. But maybe there is some sort of salvage that one could do. Instead of direct products, there might be some other operation that does that job. That is also in general not true, but there are some groups where we can do replace a direct product by what we call a semi-direct product and prove something of this form. So we might get there, but so this is too strong, but we are going to be able to prove these two big theorems, Cauchy's theorem and the first Sylow theorem, and then the second and the third Sylow theorems, using essentially just group actions. So let's define what a group action is. So before we define group actions formally, let me just say that some groups naturally act on certain sets. So for example, so here are some examples of groups that are acting or transforming sets. So for example, S4 acts on the set of 1, 2, 3, and 4. What do I mean by that? Well, if I have some sigma in S4, let's say, for example, sigma is 1 2, 3, 4, this permutation, then, well, sigma acts on, for example, the letter 2, the number 2, and it sends it to 3. Or sigma acts on 1 and sends it to 2, and etc. It just acts on the set. It just tells me how to define an action or define some sort of like uh, um, discrete dynamical system on these letters. So sometimes we write 1, 2, 3, and 4, let's say, and actually it might be better to write them sort of in a circle way, 3 and 4, and then if I have sigma, and sigma is the permutation 1, 2, 3, 4, we're going to draw diagrams that tell me how the action works. 1 is being sent to 2, 2 is sent to 3, 3 is sent to 4, and 4 is sent to 1. So that is the diagram for that permutation. If I pick some other permutation, for example, 1, 2, 3, 4, then this has a different diagram. This one sends, well, 1 is sent to 2, but 2 is sent to 1, and 3 is sent to 4, and 4 is sent to 3. So it has a different diagram, but it just gives you a sense of how this group is acting on a set. Let me give you another example. The matrices, the 2 by 2 matrices with non-zero determinant, they acts on R2. How does a matrix A, B, C, D act on a vector? Well, it just sends a vector to another vector by the matrix multiplication. This is AX plus BY, and CX plus DY is the effect of that matrix on that vector. And for example, I have here 1, 1, 0, 1, for example, is a matrix. How does it act on 1, 0? 1, 0 is sent to itself, but however, if I act on 0, 1, I go to 1, 1. So it acts, what do you say, trivially on 1, 0, but non-trivially on 0, 1. So if you want, you could draw the vectors. Let's draw here the vector 1, 0 and 0, 1, and the action is going to send 1, 0 is being sent to itself, but 0, 1 is being sent to 1, 1. So there's the other vector that is involved here is 1, 1. And this one is being sent to that one. Okay, what else? There's here's another action. A natural action is Z modulo 2 acts on the complex numbers. Really, how so? I'm thinking of Z modulo 2 as 2 elements: the identity automorphism of the complex numbers, and tau, which is so this is just identity, the identity map, while tau is complex conjugation. So the identity acting on any complex number, it just sends it to the same complex number, but the complex conjugation sends A plus BI to A minus BI. If you draw again what's happening in the complex plane, then let's say what is happening with tau. So here I'm drawing the action of tau of complex conjugation. Then any vector or any complex number here is sent to its complex conjugate. So if this is A plus BI, it is sent to A minus BI. So this complex number is going there, and this one is going over there. However, if you have a number on the real line, then those are actually sent to themselves. Okay, so if this is just a real number with, oops, let's put it in green, uh, a real number A, then they're being sent to themselves. Okay, so what is a group action? So here's how we define a group action. So let X be a set and let G be a group. Then a left action, there's also right actions. So, but usually when we say action, we mean a left action of G on X is a map from G cross X, from the direct product of G, the group, and a set X to X, such that for any pair of element of the group and element of X, sends it to G times X. This times is how we're going to define the action of G on X. And this has to be a new element of X. Okay, so there is, in fact, three things to check for a group action. First of all, that G times X is always an element of X. That is important. And second, we require that the identity acts as the identity. The identity on the group acts like the identity, that E dot X is X itself for every X in the set. And second, we want the multiplication to work as follows. If I have two elements of the group, G1 and G2, I want the product. This product is the binary operation on G, which is a group. G1 times G2, I can multiply them first and then see how the product acts on X, or I can act with G2 first and I can act with G1 later, and that should be the same answer as if I do this first. So that has to happen for every X and for every pair of elements of G. If so, if these three things happen, then we say that G acts on X, or that X is a G set, or sometimes we write this, that X is acted upon by G. Let's see some examples. Let's prove that the action we defined before, the action on matrices acting on vectors in R2, that is an action defined by, again, how do we define the action of a matrix on a vector? That is just ax plus by cx plus dy. That is an action. First of all, notice that ax plus by cx plus dy, it is also an element of R2 for all a, b, c, d in GL2, and for all x, y in R2, I do get a new element of R2. That's the first part of a group action. Then we want the identity to act as the identity. So let's see what happens when I act with, whoops, that's not the identity. If I act with this on xy, I get xy. So this is true for every xy in R2. So that works. And two, now I want to show you that the multiplication is associative in the following sense. So let A and B be in GL2R. Then I want to show that if I multiply two matrices and then act on XY, that should be the same as if I first act with B on XY and then act with A. Why is this true? This is true because of the way matrix multiplication is actually defined. Matrix multiplication, the multiplication of two matrices, is precisely defined so that this happens. Why is that? This is because the matrix A can be thought as a linear map from R2 to R2, and similarly, the matrix B can be thought of a map from R2 to R2. And if you do the composition of these ones, in this case, first with B and then with A, I have X. These will go to B times X, and these will go to A times B times X. And this map, the composition from here to here, is actually defined to be, or the matrix multiplication is defined to be, so that this is A times B times X. So this is true because of the very definition of matrix multiplication. And that holds for every pair of matrices and for every vector. So this also holds. So this is a group action. Let's see another example. For example, let's go back to S4 acting on 1, 2, 3, 4. Certainly, if sigma is in S4, then sigma of I belongs to, this is X, this is also in X. It sends one of the numbers 1 through 4 to one of the numbers 1 through 4. So that is part 0. The action is well defined. So this is what we would say is sigma acting on I, on the letter I, for any I in X. Now, is identity acting as identity? Sure, there is an identity, which is the identity permutation in S4. The identity acting on I precisely sends it to I for all the I's from 1, 2, 3, 4. So it works. And second, let's see, if I have a sigma and a tau, let's say in S4, is it true that sigma tau acting on I is the same as sigma acting on tau acting on I. And this is true simply because the multiplication, the binary operation on S4 is composition of permutations or of automorphisms of X or symmetries of X. So because it is composition, this is precisely how composition works. So this is the composition of sigma and tau, and this is the composition of sigma and tau. So it works. Okay, okay, and okay. Let's see a little bit more sophisticated example, which is some of the examples that actually will be very important when we talk about group actions and we try to prove things such as Cauchy's theorem. For example, I can take now, G is going to be a group. Let G be a group. And let X be the same group G. And then G is a G set. So G acts on G via what we call the left regular representation of G, which is the following, is a map from G cross X to X, but just remember that X is G itself. So we take an G and let's say another element H of the group, and we just send it to G acting on H is going to be G times H. Notice that this dot here, that is the action. That's how we are defining the action. But over here is just multiplication in G. Okay, so just multiply on the left by G. So let's check that this is a group action. 0 for all G in G, and for all G in for H, in X, which is also G, G dot H is G times H, which is also in G, which is X, because the multiplication is closed, because G is closed under the binary operation on G. So G times H is back in G. Okay, 1. Now let E be the identity in G, Then E dot H is EH, which the identity, by virtue of being the identity, just gives you H back. And this is for all H's in X, which is the group G. So it works, that identity works like the identity. And second, now let G1 and G2 be in G and H be in X, which is G. Then how much is G1 acting on G2 acting on H? The first action, the action of G2 on H is just G2 times H. Then the action of G1 on that is just multiply on the left by G1, and I get this. But this is G1 times G2 times H, but by associativity of the multiplication in G, of the binary operation in G, I can rewrite this as G1 times G2 times H. And again, here I'm using that star is associative on G, and this is the same as G1, G2 acting on H. So it also works. So all three properties are satisfied, so this is a group action. Let's see another one, a different action of G acting on G, which is via conjugation. Now I'm going to take my group. So let G be a group, and let H be a subgroup. Then H acts on G via conjugation. So here H is the group that is acting, and the set X is a group G. Okay, so H is acting on X, which is a group G, and defined by, so how are we acting? An H, or let's write the map itself. So the map goes from H and G to G, and if I have an H and a G, I'm going to send it to the conjugation of G by H. Okay, so first of all, 0 for all G in G and for all H in H. Notice that HG, H inverse is still in the group, so the map lands where it's supposed to land. H times G times H inverse is still in the group G. Okay, 1. Now for all G in G, if E is the identity element on G, which is actually the same as the identity element in H because it's a subgroup, then what happens when I act by this element? So E acting on G is E, G, E inverse. The inverse of E is E. This is E, G, E, and multiplying by E on the left or the right, it doesn't do anything other than I get back G. So that works, this works, and now the associativity. So now let G be in G, and let H1 and H2 be elements of H. Then let's see how much is H1, H2 acting on G. if I act on G by the product H1 times H2, then I'm conjugating by H1, H2 times G times H1, H2 inverse. Now these are the stars. So this now is multiplication in all happening in G. Okay, this is also H1, H2, G. The inverse of a product is product of the inverses in the opposite order. So this is H2 inverse, H1 inverse. And now you can see that inside here, this is H1, this piece here, this is H2 acting on G. This is the conjugation of G by H2. So this is H2 acting on G. So I'm going to write that as H2 acting on G, and then I'm conjugating with H inverse. But that is now, this is H2 or H1 acting on H2G. H2 acting on G, in fact. So this is H1 acting on H2 acting on G as we wanted. So this is also a group action. Another example. I think I'm going to do a couple more examples. Let me give you first this one. So let G be a group. And let N be normal, or a normal subgroup. Then G acts on N via conjugation. So the map is now from G cross N to N. So the set is N, and G acts on N via conjugating. First of all, is this a set, an element of N? So for all G in G and for all N in the normal subgroup, we have that, because since N is normal in G, we know that G and G inverse is N by one of the conditions that were equivalent to being normal, and therefore G and G inverse is in N. It doesn't have to be little n, it is in capital N. So it is well defined. The map sends something in G and something in N to something that is in N, which is this conjugation. 2 or 1. Now let's take E, the identity, and let N be an element of N. Then, well, E and E inverse, once again, that's just N. So identity acts like identity. And 2, now let's see what happens if G1 and G2 are in G and N is in N. Then if I act by G1 times G2 on N, then I get G1 times G2 and G2 inverse. And this is, sorry, no, I don't get that. I first get is the product acting on N. So this is G1, G2 times N times the inverse, which is G2 inverse, G1 inverse, and this is an N. Okay. So, and now I can rewrite this as G1 acting on, by conjugation, on G2 and G2 inverse, G1 inverse. So this is G1 times G2 acting on N, G1 inverse, which is the same as G1 acting on G2 acting on N, which is what I wanted to prove the sensitivity of the action. Okay, so I get an action from G acting on N as long as N is normal. If N is not normal, if N is any subgroup of G, this would not have worked. this, if H is not normal, when I conjugate by just any element of G, it doesn't have to stay in H, but it only stays in H because the subgroup itself is normal. So G does not act on just some random subgroup H via conjugation. It only acts on the normal subgroups. Okay. One last example for you today is the following. So if H is a subgroup, any subgroup now, and let G mod H just to be the set of left cosets. Let me write that right. The set of left cosets of H in G, then this does carry an action of the group itself. How? Then G acts on the set. H is not required to be normal, so this is just a set. G mod H is not a group unless H is normal, but just on the cosets, how am I going to act? I'm going to go from here to, I have to get a new coset. So here's how we're going to define it. So all the cosets look like this, and then I'm going to send it to GKH, to this new coset. And you have to actually prove in this case that this is well defined, because I've defined the action on a representative, of a particular representative of the coset, and got a new coset. So if I picked a different representative for this coset, do I get the same coset? And the answer is yes, and you can check that that this is independent of the generator I picked. If there's another generator of this coset, they differ by the generators themselves basically differ by an element in H, and you're going to end up getting the same coset over here. As an exercise, check that this is, so check one, that this is well defined, and two, that this is a group action. So this is an exercise for you. Okay, so next time we will prove properties of group actions.